Good morning, everyone. I am Dr. Sravanthi from Department of Aeronautical Engineering. So today we will be discussing another topic from our second module, right? So that is geometrical sizing and configuration layout. Okay. So geometrical sizing of a fuselage, of wing, of tail, and of control surfaces, right? So today we will be covering all these four topics, and then we will go to the configuration layout, and we will also see the lofting, right? Geometrical lofting. So before we start with this particular geometrical sizing of fuselage, wing, and tail, what is it we have done in the previous classes is we have calculated the takeoff gross weight, right? So takeoff gross weight estimations have been done for in the first module we have done it without having a weight drop or a payload drop, and by normally we have calculated the takeoff weight estimation by doing all the segment fractions, which is wx by w naught, right? We have multiplied all the segments of a particular profile, then we have calculated the fuel fraction, right? Then we have calculated the empty weight fraction, correct? Then with these empty weight fractions were coming from the historical trends. So we have taken the particular type of an aircraft, we calculated the data, and finally we have written W naught, alright, so the takeoff weight, and we have done some iterations by guessing it and by calculating the W by W naught, and then from there we got finally the W naught calculated value, right? And we need to continue guessing the weight until we get a closure or approximate weight for a calculated W naught, right? So that is what we have done. And in the next, we said that it should be a refined sizing. Refined sizing includes whether if it is rubber engine sizing or if it is a fixed engine sizing, right? Fixed engine sizing is where all my parameters are already fixed. I'm not going to change any of the thing, thrust to weight ratio. Whereas the rubber engine sizing is where I have a opportunity, or I could stretch the parameters and change few things, right? So that is your rubber engine sizing. And when we were talking about the rubber engine sizing, we said that it has to be the calculation of the weight, takeoff weight has to be in a different way. Different way is I also need to consider my weapon drop. Correct? He said that if there is a payload drop, if there is a weapon drop, then that particular segment also need to be considered, also need to be calculated, and accordingly the fuel, whatever is going to be consumed, we need to make all those calculations precise, or in other words refined, then come with a proper size, right? So what is that we have said? Just see the different steps that are included in that particular, right? So we said that if I have to talk in terms of a refined engine sizing, then it has to be like you start off the engine, right? Engine start and take off. W1 by W0 is going to be the same, where it is a fixed value. Then when you're talking about the next segment, which is climb and accelerate, then here we are going to consider in terms of a Mach number, right? Mach number with respect to flying at a subsonic or flying at a supersonic regime as you're trying to climb and accelerate. So at different regimes, considering the Mach also, we are trying to refine the sizing, right? Then cruise and lighter again goes with the same Burgert equations, right? So we had a Burgert range equation, we had a Burgert endurance equation. With respect to that, we are going to calculate our cruise segment or a loiter segment, right? Then in this we will be having a combat, right? So when you're talking about a military application, then military applications has a combat. So in the combat combat mission segment includes this particular equation, right? So where you're talking about the time duration, you're talking about the power out, like that, right? Then we had a descent and landing, right? So descent and landing are again in terms of how we are going to calculate, right? You take the segment fraction and you do all of these things, then calculate empty weight fraction, calculate your fuel fractions, and also do the iterations, right? Then come to a conclusion of how it was going to be, right? We have taken a numerical, right? So numerical is being considered DR3, a lightweight super cruise fighter. Now for this particular fighter aircraft, we have calculated the sizing, refined the sizing, right? So the segment includes 14, right? For the 14 segments, for all of the 14 segments, the data has been given. For that particular data, we have calculated the empty weight fraction. So empty weight fraction was going in terms of whether it was a trainer or fighter aircraft, and accordingly, the all the constants are given, and we go and calculate empty weight fraction. Then we have calculated the climb and accelerate. Right, climb and accelerate. We're going with respect to subsonic and supersonic. We need to calculate the wing loading, and then finally we come up with the range in terms of cruise or in terms of loiter, and then descent and landing, right? So this is what we have done in refined. So now we will be talking about this particular geometrical sizing of fuselage, of a wing, of a tail surface, and the control surfaces, right? Now when you have to do a sizing of a fuselage, many methods are there. Many methods exist to initially estimate that particular required fuselage size, right? But when you are talking about certain types of the aircraft, fuselage is going to be strictly by a real world constraints, right? So this is when we talk about a commercial aircraft, my aircraft is going to take the major portion of it in terms of a fuselage, right? So the major area is going to be covered with respect to the passenger compartment or with respect to the fuselage section, right? So when you know how many passengers are going to be accommodated for that particular aircraft, or the number of the seats, right? How many passengers with respect to number of the seats, then that is how your fuselage length and diameters are going to be determined, right? Because my commercial airways or my commercial aircraft is going to be designed, or the major portion of it is going to be taken by the this particular fuselage section or the passenger compartment, and with respect to that I need to check with the number of the passengers or the number of the seatings, right? Then accordingly you go and size, right? We are talking about sizing here, so accordingly we make the geometry sizings of a fuselage. Then the initial guidance during this fuselage layout and also the tailing size is to be considered, right? So data has been provided for it. Now these are again based upon your the takeoff gross weight, whatever we have been calculating for different aircrafts, right? So we have considered few examples, and for those we have estimated the takeoff gross weight, that yes, my aircraft upon having a different segments includes your cruise or climb, or if there is a loitering, right? Or if there is a particular payload drop or whatever, we're talking about the refined sizing and how we go and calculate the takeoff gross weight. And that should include your fuselage layout or tail sizing in initial condition. That is what I'm going to expect, right? So that should give the good relation to most of the existing aircraft. Now again, the fuselage finish ratio is a new terminology. So fineness ratio is a ratio between the fuselage length and its maximum diameter, right? So first of all, I need to estimate what is the fineness ratio of the fuselage, right? Now this is important when we are talking about the commercial airways, right? Now in the commercial aircraft, all want to accommodate is the passengers, right? And there I would want to know or size the length of it, right? What would be the length? What would be the diameter of it? So therefore, my finish ratio is important here. So calculating the fuselage finish ratio. Then if the fuselage cross section is a not circle, an equivalent diameter is calculated from the cross sectional area. Okay. So that is how we go and calculate the sizing of a geometry of a fuselage. Then next is the wing. Now wing, when you're talking about the wing, the actual wing size can be determined simply by the takeoff gross weight divided by the takeoff wing loading. Right, wing loading we have said W by S, and we also seen how to calculate the wing loading with respect to the entire aircraft or with respect to the segments, right? So when we know the wing loading of an aircraft, we have for a particular segment. If I have to find out what is my wing loading, we have multiplied the other sections fractions with respect to the entire aircraft, and we have calculated the wing loadings of that particular segment, right? So when you are going to size the wing, it is going to be determined with respect to takeoff gross weights divided by the takeoff wing loading. And this is particular table is been taken from the Raymer textbook. It has been taken from the previous trends, right, historical trends, in order to calculate the fuselage length with respect to your takeoff weights, right? So my fuselage length versus W naught is going to be, length is going to be A into W naught power C, right? Now A and C are again a constant figures here, right? Now when A and C are constant figures, for a different type of aircraft, is if we are talking about the flying boat, or if we're talking about the fighter aircraft or a jet transport. If it is a fighter aircraft, then this is what my A and C are going to be for in order to calculate the fuselage length, right? Then a tail volume coefficient. Now I know how to calculate the fuselage. I know what to do with respect to the wing. We need to consider the wing loading, and we also have a table which would give the constants for in terms of fuselage length, right? So then coming to the tail volume coefficient, right? For the initial layouts, right? Now it's not just that designer come up with a particular design and that is going to be the final approach. No, right? In the first module we said that design is being categorized into conceptual stage, preliminary stage, and detailing stage, right? In the conceptual stage, he come up with an idea of what has to be done, how it has to be done, or what are the different requirements, or what are the different parameters that need to be considered. Then in the next stages, it is going to be initiated, right? You come up with various approaches to it. You try to sort things out, right? Other designers or other specialists are involved in it. Then finally, a detailing of each and every component is being done, right? So as such, in the initial layout, I am dependent on the historical approach only. I cannot just come up with a new approach, right? So new approach would take expensive or a time, right? And therefore a historical approach is the it's already existed. I know what parameters need to be considered here, right? So in the initial stage, or in the initial layout, a historical approach is used in estimating the tail size, right? Now the effectiveness of a tail in generating a moment about the CG is proportional to the lift that is going to be produced by the tail and its tail moment arm. Now, the primary purpose of a tail is to counter the movements which have been produced by the wing only, right? Now, then it is expected that tail size is going to be related to the wing size only, because both are in correlation. They have to counter the movements that are going to be produced by the wing, right? So the tail area is divided by the wing area should show a consistent relationship for a different aircraft. Now the force due to the tail lift is again proportional to the tail area, right? Then the tail effectiveness is proportional. Again, it is proportional to the tail area into the tail moment arm, which is L. Now this will give the tail effectiveness is going to be proportional to the tail area times the tail moment arm, right? Now this has units of volume which would lead. So that is why we are talking, or we are calling it as a defining in terms of a tail volume coefficient method for a initial estimation of tail size, right? Now then again we are again categorizing this in terms of a vertical tail and a horizontal tail, right? So for a vertical tail, the wing yawing moments, right? The yaw moments which must be counted are directly related to the wingspan VW, right? So these are related to the wingspan. The yaw moments are related to the wingspan, which is called as a vertical tail coefficient. And for a horizontal tail, it is a pitching moment, right? For a pitching moment, it is related to the CW, which is the mean chord, right? Wing mean chord. Then it is called as a horizontal tail volume coefficient, right? So CVT for a vertical tail volume coefficient, it is LVT by LVT into SVT by with respect to the this particular wingspan into SW. Then if you're talking about a horizontal tail volume coefficient, it is LHT into SHT by CW wing mean chord into SW. Right, so for initial sizing, this is how I go and estimate the tail volume coefficient method with respect to all of these things. So this is your LC, then LHT, LVT, vertical tail, horizontal tail, with respect to the chord. Right, so SW is a wing area, BW is a wingspan, CW is a wing mean chord. Now again, for a tail volume coefficient also, I want the horizontal with respect to horizontal, with respect to vertical, CVT and CHT, and for that we have a table from Raymer. So taken from the past trends for different type of an aircraft, I have different CHTs and different CVTs. So if I go and substitute, I should be able to calculate the tail volume coefficient. So this table is going to give the values for a volume coefficient for different types of an aircraft, right? So upon these, we should be able to calculate the tail areas, right? Or to calculate the tail size, the moment term L must be estimated, which is approximated at the design stage. So I am trying to estimate this during the design stage itself. So SVT for a vertical tail, SHT for a horizontal tail. For a vertical tail, it is going to be CVT into BW into SW by LVT. For a horizontal, it is going to be CHT into main wing chord into SW by LHT. Then that is how we go and size the geometrical sizing of a fuselage or a wing or a tail, right? For a fuselage, I should know what is the length and what is the diameter. Then I go and calculate the fuselage spinach ratio. Then I also know with respect to the fuselage length and cross weight, takeoff weight, I have the parameters that are constants for different type of aircraft. I consider from there and I calculate the fuselage geometrical sizing. Then with respect to wing, also same. Again with respect to tail volume coefficient also, we take upon the all main chord or wingspan. Then we calculate the horizontal tail and a vertical tail coefficient with respect to yawing movements and the pitching movements. Right. The next is your control surfaces. Right. Sizing of control surfaces. So the primary control surfaces we all know: aileron, elevator, rudder. Ailerons for rolling movement, elevators for a pitching movement, and a rudder for a yaw motion. Right. So final sizing of these surfaces is based upon the dynamic analysis of a control effectiveness, which should include the bending, structural bending, and control system effects, right? The effect of the control system and also the structural bending of it, right? So figure shows the aileron guidance here, right? Aileron guidance can be seen. This is the historical guideline, how my aileron chord with respect to wing chord is there. The required aileron area can be taken from the figure, right? So whatever the aileron area you want, that should be taken from this aileron guidance. Then in a span, the ailerons extend from about 50 to 90% of the span if we're talking about the span only. Then wing flaps. Now when the flaps occupy the part of the wingspan inboard of the ailerons, right? If a large maximum CL is required, if I want a maximum CL, then I want a flap span should be as large as possible, right? So first of all, if you're talking about the span, ailerons are going to be extended from 50 to 90 of the span. Then flaps are going to occupy the part of the span here. Now, if a maximum CL is required, then the span, it should be as large as possible, right? Then for that, let me use the spoilers rather than ailerons, right? So it would be better if there are spoilers. Then the spoilers are plated, located forward of the flaps on the top of the wing. So typically they are aft of the maximum thickness point. Then these spoilers are going to be deflected upward into the slipstream in order to reduce the wing length, right? So these control surfaces are tapered in the chord by the same ratio as wing or tail surface so that they maintain a constant percent chord, right? They need to maintain. First of all, if I want a maximum span, if I want a maximum CL, I want a huge span, large span. For that, instead of having an ailerons, let me have a spoilers, right? And development of a configuration layout from a conceptual sketch, right? So up till now we have been talking about the conceptual sketch or conceptual design of an aircraft, right? Now developing the layout of it, right? So whatever the designing or sizing of the aircraft with respect to conceptual stage we have said, That should include all the numerical statistical estimations, right? We have done estimation of takeoff weight of a fuel, of an empty weight, and we have calculated the gross weight, right? All these are numerous statistical estimations, then analytical predictions and numerical optimization. The number of optimizing, you are trying to optimize things a number of times, and you're trying to come up with your what is required or what is want, right? So now, but even when we're trying to say that aircraft sizing or in terms of conceptual stage or conceptual design, it would include all these estimations, all the analytical predictions and the optimization. But however, the product of aircraft design is a drawing, right? You need to have a layout in the hand, right? And I want to know exactly where all the different components are going to be placed, how all of them are going to be accommodated in that particular huge aircraft, right? So at the end, it is going to be a developing your layout or development of a configuration layout, right? So while the all these analytical tasks are important, all of these are important, right? So how much the fuel has to be consumed, or with respect to that particular range, or when you're trying to climb and accelerate, or when you have a loiter for 30 minutes or for 20 minutes, or if there is a weapon drop, right? All these estimations need to be done. Yes, all the analytical predictions have to be done. All the sizing specialists have to check for all those validations. Yes, all of them are important. Designer must remember that all these are going to influence the drawing only, right? For it is the drawing alone that ultimately will be used to fabricate the aircraft, right? Now, when all of those things are done, right, when I come up with in the conceptual stage, when I'm making few estimations, when I'm doing few analysis by doing iterations or by optimizing the things, right? All of these things are going to end up having a drawing in the hand or having a configuration layout of it. Only when configuration layout is correct, only that particular layout is going to be fabricated, right? So that is what my fabrication stage begins, when it begins, right? Now all of these analysis effort to date are performed to guide the designer in the layout of initial drawing. Now all these are only up to initial drawing. It's not just so all of these things have been cleared, then that is the final drawing, that is where finally the fabrication is going to begin. No, that is the initial drawing. Now once you complete with that initial stage of drawing, a detailed analysis can be conducted to resize the aircraft and determine its actual performance, the efficiency of it, or we don't say efficiency, we talk in terms of performance, right? So the performance of the aircraft need to be measured, and that comes by sizing again and again, or configuring, right, the optimizing things, right? Coming up with initial drawing and then try to refine it, and then we have a stage where yes, this is what the customer has asked for, and this is what has been concluded, or this is what we have finally come up to a point that yes, this is what has been output that for the objectives that are being present, right? But again, detailed analysis is a time consuming and again very expensive, right? So now the end products of the configuration layout. The output of the configuration layout task will be the design drawings of several types as well as the geometric information that is required for the further analysis, right? So design layout process generally begins with the a number of sketches, right? I would have quite a number of conceptual sketches. Now example has been taken, right? Now figure is showing a fighter conceptual design study, right? Now this is my fighter aircraft where the designer has made a conceptual stage or the initial sketch of a fighter aircraft, right? Yes, this is how the aircraft should look like. Then all the sketches are crude and they're quickly done, but they are going to depict the major ideas which the designer intend to incorporate into the actual design layout, right? So the first stage or the first sketch should predict how it has to be, or what are the different major portions where all they setting up, and what is the requirement, or all the objectives are going to be filled in that particular requirement, right? Are they going to fill it up or not? So majorly he is going to briefly tell that yes, this is what it is going to look like, right, in the initial sketch. Now then figure 2 is going to be the actual design layout, right? So figure 2 includes a lot of things, right? So I have a quite number of sketches here, right? where I try and make all the different parameters or configurations or all the sizings, all of the detailing is been going in the second stage or second sketch, right? Now figure 3 shows the initial design that is going to be developed from the figure 1, right? Let's see. Yeah, so this is how now it has been a little neat, right? So from the first figure, what we see is just a rough idea or rough sketch of what has to be done, the major idea of it. And the second sketch is where I'm trying to sort things out. I'm trying to put all the components or all these things have to be in this way, or the sizing has to go in this way according to the fuel consumption or according to the weight or according to the thrust to weight ratio, right? Then third stage would look like this CAD one, right? Computer aided designs, right? So this is how finally it is going to look like, right? Now then we have a figure 4, which is inboard profile, right? So this design layout from second and third figure shows the primary input to the analysis and optimizing task, right? So once the design has been analyzed, right? Once you have all the specialists and all the designers included checking their individual portions where propulsion or for the flight dynamics or stabilities and control or the aerodynamics, right? Individual designers are going to check their areas and analyze them and optimize them and trying to sort things over there, right? And redrawn for a number of iterations of the conceptual design process. A detailed drawing can be prepared, right? So you come up with a rough sketch, you try to sort things out, you're trying to analyze them, optimize them. So a number of sketches have been made, right? So finally a detailed drawing has been prepared. Now that is been shown in the figure 4. The inboard profile drawing depicts the internal arrangements of the subsystems. Right. So this is my figure 4 where I know yes a cockpit with a fuselage, the length of it, right? Then the diameter of it or the propulsion unit of it, how it is going to fit in the tail portion or the wing portion, right? Or the landing gear portion, right? So all of them are being properly arranged, the subsystems of it, right? Now I know where the subsystems are going to be fitted in according to the aerodynamics aspect. So the inward profile is more detailed than the initial layout, right? An example is taken. While the initial layout may indicate a avionics bay based upon the statistical estimate of the required volume, the inward profile drawing will then is generally a team project and takes many weeks, right? During the preparation of a profile, it is not uncommon to find that layout must be changed to provide enough room for everything, right? So as a result, it is imperative that the initial layout will be as well thought out as possible. That means, see here, when we have seen an initial sketch, my initial sketch would look like this, right? I just know that, yeah, this is how it has to be. But then you try to go and configure things, then you're trying to optimize things, analyze them, optimize them, and then you finally come up to a point where, yes, this is how the aircraft is going to look like with all the subsystems included in it, all of them running well according to the good aerodynamics, good flight mechanics. And this would take time, and there should be room for all of the components all going correct. Only then I see that there is a maximum CL or what are the requirements that are been set given by the customer. So that is what we're trying to fulfill it here. Right? So that is what a figure 4 inboard profile should look like. Right. So next is the lofting. Right. Now lofting is a process of defining the external geometry of an aircraft. Right. So in that we have a production lofting. Now when we say production lofting, the most detailed form of a lofting, right, which provides an exact mathematical definition of entire aircraft, including the minor details as intake and exhaust ducts of the air conditioning. Right. So that means lofting is what, it's not that only one person is going to design the entire aircraft or one person is going to analyze the entire aircraft or the entire subsystems of it or the systems of it, right? So there are different specialists, there are n number of different designers or the specialist or the analyst, right? So who are going to design the separate portion of a particular aerodynamics, or they're going to test it or analyze them and optimize things. And then we have people, a different set of people in terms of propulsion, right? Who's going to look after the engine units or consider that particular propulsion of it or analyze things design it, analyze things, and trying to optimize it, right? So same way with respect to other stability and control, right? There are different major systems to n number of subsystems, right? And all of those things are not going to be done by one particular person or one team or not at one place, right? Individually we have separated them, and all these things have been done by different people in different areas. But when you finally try to arrange them, right, when you're finally trying to put all of these things together, it has to be precise, right? So that is where the word comes lofting, right? Lofting is a process of defining the external geometry of the aircraft. Okay. A loft is expected to be accurate to within a few hundredths of an inch over the entire aircraft. This allows the different parts of the aircraft to be designed and fabricated at different plant sites, yet fit together perfectly during final assembly. When you're finally assembling all the subsystems to a smaller components to a subsystems to a major systems, all the things should fit perfectly, right? So then most aircraft companies uses the computer aided loft systems, right? So the overall lofting of the fuselage, wing, tails, and nacelles must be defined sufficiently to show that these components will properly enclose a particular internal components, right? Whatever you're trying to design a small component has to fit into that major subsystem, and major subsystem into a full system or a final systems, right? Now, to provide a smooth longitudinal contour, points taken from the desired cross sections were connected longitudinally on the drawings by a splines, a long thin wood or a plastic rulers held down at a certain points by lead ducts, right? So these are been shown here, spline lofting, right? Where I have no known points and where I have lead ducts. Then the wetted area, right? So aircraft wetted area, which is SWET, the total exposed surface area that can be visualized as the area of the parts of the aircraft that would get wet if it was dipped into the water, right? So the wetted area must be calculated for a drag estimation, right? In terms of skin friction drag. The wing and this tail wetted areas are approximated for their planforms, right? So now the effect of the final thickness is to increase. I want to increase the wetted area. The true exposed planform is projected area by a cosine of the dihedral angle. Just regarding these wetted areas, we have discussed in the numerical approach, right? So when we're trying to estimate the takeoff weights, we have calculated the S weights. So my S weight of the thickness to chord ratio, if it is less than 0.5, then my S weight is going to be 2.00003 x exposed. Then if it is if the thickness to chord ratio is greater than 0.05, then the formula is going to be in this way. Okay, so aspect, fuselage bedded areas. So all these are the different approaches to calculate it. Okay. The more accurate estimation can be obtained by a graphical integration using a number of. You try to take number of fuselage cross section and you try to obtain it by graphical integration, right? So here a crude estimate of internal volume can be made using the L in the fuselage length. Okay, so that is where we stop today, right? So all we have seen is how to size the geometrical sizing of a fuselage, of a wing, of a tail, and then finally the control surfaces of it, right? Control surfaces also have to be sized in a very well. Then finally it was about lofting, right? So lofting or a conceptual drawing, right? So all of the analysis or all the optimization or all the estimation, statistical estimations were done to finally come up to a point of having a initial layout or a sketch. Then finally sketches have been come to a point where it has an inward profile where all the subsystems are properly well designed and well analyzed over there. And then finally it was been sent to the lofting or where lofting has been done, right? So all the set of components have to be entirely have a perfect assembly to it, right? That is lofting. So tomorrow we will see in detail about the lofting. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.